So welcome back. There was actually an interesting question during the break, and I can also say a few words about this, about how to use in practice. And the idea is that you might have data sets in your semester project or in your master's thesis that you need to analyze, and it's typically going to be files, right? In that example, it was hundreds of files that contains a table in the same schema, HDF format. And the idea is that you should, if you're going to do a lot of queries and a lot of analysis, there is a fixed cost to getting it into PostgreSQL. You will have to find out a few tools that allow you to import, possibly with pandas and so on. But once it is in PostgreSQL, then things become easier because you can just sit and type some SQL in your Jupyter notebook and see the results. You can build indices on the tables that accelerate the queries and so on. So things become faster. And then at the end, also with using Jupyter notebooks, you can re-export some aggregated data and plot it in Python, right? But having in the middle the data stored once and for all, it's just once and for all, you put it in PostgreSQL, then things are going to become easier. And so the idea is that it's a fixed cost, dynamic cost thing, is that if the query you want to do is just one and it's very simple, then go ahead and do it in pandas. Don't even bother to import into PostgreSQL. But if you do want to do heavy analysis for a period of time and write plenty of query, then the efforts and fixed cost of getting it into a PostgreSQL table are really worth it, because then you can just use SQL to query it, right? So that's the typical goal of the course, is to give you these insights so that you can use it concretely, right? And as we'll see in a few weeks, SQL is part of an ecosystem. You don't do everything in PostgreSQL, right? It's typically used in conjunction with Python, in conjunction with visualization tools, in conjunction with importing tools, right? So yeah, I think it was interesting to share with the class as well. All right. So there was a question during the break about repeating what I was saying about that part right here, right? So these kinds of predicates. So this slide refers to specifically what you can have in the from clause, right? And in the from clause, you can have a single table name, or you could have joins. And on the left, so that I think you got, right? All the kinds of joins you can do. And on the right, you have the several options in conjunction with what there is on the left. Either you make a natural join, or you specify a few attributes that you want to join on, or you specify a more complex predicate that you want to join on, right? So if you want a natural join, you would just put the keyword natural before here. You would say natural join, natural left join, natural right outer join, right? You would just put the natural in front, and it's going to just match the records based on all the columns that are the same in both tables, right? But sometimes you might have column names that are the same by accident, and you don't actually want to match on these columns. So in that case, instead of natural, you can use using instead of natural, and then you specify these attributes that you want to join on, and not include those that you don't want to be part of the join condition, right? So then you switch to using. It's kind of a natural join, but restricted to the attributes that you want. So natural is in front, using is after, right? So natural would be here, using and on would be on the right. So you would say table, left join, other table, using, blah, blah, blah. And finally, on and a predicate corresponds to the theta join. The theta join is where you have this horizontal hourglass, right? The X with two vertical bars, that is the symbol for the join. The difference between the natural join and the theta join is that the theta join has a subscript below that symbol. And the predicate after on corresponds to that subscript, right? So if you have a join symbol subscript predicate B, then that would translate into on with the predicate in SQL, right? Does it make sense? Does it answer the question? Yes. Right. Awesome. So you see, you have 13 combinations in here. 13. You have 4 times 3, right? So inner, left outer, right outer, full outer. That's 4 of them, times 3 because you can combine them in any way you want. So that's 12 possibilities, plus the Cartesian product, cross join. The cross join doesn't have, of course, natural using and on because that's something else, right? So just the Cartesian product. So that's 13 possibilities. To which I might add, if you remember from last week, that there are people who do their joins not in this way. They don't use the explicit join keyword. They prefer to write a Cartesian product in the from clause and to specify the theta join criterion in the where clause, right? Technically, that would be a selection after a Cartesian product. But the magic is that PostgreSQL recognizes the join. It understands what you want to do, and internally it's going to rewrite it as a join. That's the power of a declarative system like this, is that SQL will not do the actual Cartesian product. It will execute it as a join, even if you use from and where. Okay. Everybody with me? Right? All right, so then we are going to move on to database design theory. It's again going to be heavy math. That's perfect for Halloween again. So where are we? Well, we define relations as sets of maps, bags of maps, or lists of maps, depending if you like chocolate, vanilla, or strawberry. So these 3 flavors. And then we saw that we can manipulate them like mathematical objects, right? Similar to manipulating vectors in vector spaces. Then we manipulate tables with the relational algebra, and we can do all kinds of things with them. We can join them, union, intersection, selection, projection, aggregation, sorting, and so on, right? So we can just calculate with tables, so to say. And we've even seen how you can write programs in SQL, queries in SQL, that do exactly this, and that it in real time display the results to you in your Jupyter notebook, right? So this is what we've seen so far. Now, technically, you already have enough knowledge to just go ahead and store data and query data, right? So imagine you're working with a company later, and or you're creating a startup, maybe a web shop. You want to sell things over the internet. You want to set up a relational database management system behind your website and use PHP maybe for the front end, or maybe Node.js or whatever technology you want, and then have a SQL database in the background. But there are a few things. You might fall into a few traps. If you just go ahead and do tables a little bit randomly. And the goal of this lecture right now is to make you aware of the do's and don'ts of how to design good schemas and the bad practices that are going to lead to problems. So I'm going to start right away with bad design for a web shop. So imagine I have a web shop, and I just went ahead and created a single table schema in my database where I have all of my customers and orders and inventory and so on. And so I can see in my table that John is ordering 1 phone for 800 francs and he lives in Zurich. Peter is ordering 2 phones for 800 francs from Bern. Mary is ordering 1 phone for 800 francs. She's from Basel. John is ordering 3 laptops for 2,000 francs living in Zurich. Mary from Basel orders 1 laptop for 2,000 and also 2 HD TVs for 1,000 francs, and she's still from Basel, right? So this is here a relational table that you could potentially use behind the website. And when people place their orders, it's going to update the table. When they register to the website, it updates the table. They change their address, it's in the table. Or maybe they use their data protection rights to ask you to delete them from the database and so on. And you just modify that table. Do you see the problems coming here? Who already starts having an intuition of why this is bad design? Not yet? So I'm going to show you. My goal is to basically give you the intuition of why this is bad design. So first, imagine that Peter just sent me a data protection request and said, I want to disappear from the database, right? So you're going to have to delete maybe this entry right here, and then information on Peter is lost, right? So if that was a data protection request, then this is fine, because that was the goal, that information on Peter is lost. But what if it wasn't a data protection request? What if Peter just wanted to cancel their order. They registered into the website and then they ordered a phone for 800 francs, but then they sent an email to say, no, I changed my mind. I don't want to, I still want to be registered, but I don't want to order the phone anymore. So then you have to basically remove that entry here. But do you see that by removing the entry, you've deregistered Peter? He's no longer in the database, right? Who sees that? Right? That's the first problem. Here, I might want to maybe Mary regretted buying that TV for 1,000 francs, and she said, no, I want to cancel my order. And so I delete the order of the high definition TV. But now do you see, I no longer know how much the TV costs, because the TV is not even on the table anymore, because that was the only order on that TV, right? So now I have no idea how much I'm going to sell it to anybody else. Who sees that? Right? So you see it starts to be a bit problematic in here, right? So now you could say, okay, if I want to delete the order, but I don't want to lose the information on the TV, what can I do? Well, I can just put nulls in here, but still keep the HD TV with 1,000 and then have nulls everywhere else, right? But you feel it's not very clean, right? It feels a bit hacky, and you probably would have to write some complex queries. You would need to test, is it the last record of the TV or not the last record? If it's not the last record, you don't do it. If it was the last one, then you add nulls. You can already imagine the complex programming that you're going to have to put in there to achieve something like that, right? Now, what if you want to update the price? You want to basically, the orders have not been shipped yet, but you made an error, you want to fix the price. So you're going to change the price right here and maybe set it to 850. But now the pricing is inconsistent, because you might have had the intention that everybody buys things at the same price, right? So if you're going to ship that phone, everybody should pay 850, right? But now we've just updated that one and we've made it inconsistent, right? So that's also a problem, that I might unintentionally get inconsistent data. Why is that? Because it's duplicated. The price appears 3 times. So it's a cognitive load that whenever you have it multiple times, if you want to change the information, you always have to keep remembering that you have to modify it everywhere to keep it consistent. Who is still with me? Right? So this is bad design. What if I want to sell a new product, but nobody has ordered it yet? Maybe I want to say to sell a USB stick for 10 francs, but nobody has ordered it yet. So I don't have any customer to put in there, right? So again, I could put null and so on. But again, it's not very clean. If I insert a customer, then I could say, okay, Bill from Lausanne has just registered to the website, but Bill has not ordered anything, so there's nothing in there, no quantity, no product, no price, right? And again, that's not very clean. So we have names for that. That's called the deletion anomaly, an insertion anomaly, and an update anomaly, right? It's when we get in trouble in this way, when we design the table in that way. And when I say in that way, we are going to define mathematically and formally what I mean with in that way, right? We're going to have the math for that. So I can, before we do the math, I can already give you an intuition of what's wrong in here. What's wrong is just that we have a table that does too much. That table has products, that table has customers, that table has orders. It just does too many things, right? So, and that's bad. You should not have tables that do too many things, not in a web shop with a database that gets constantly updated, right? And so what do people do in practice? And that's the intuition. You should just, can anybody guess? Maybe people who already saw real-life databases. How can we fix that? Yes? Yeah, exactly. Separate the tables. That's exactly the idea. You basically instead store the same information with different tables, and each table does just one thing. We have one table that only does the products, we have one table that only does the customers, and we have one table that only does the sales, right? Do you see how these tables are interconnected? Do you remember who remembers primary key, foreign key? Right? With the power of primary keys and foreign keys, I can link them, because the column product in here is a primary key, Well, of course, you would never do that in real life. You would not use that as a primary key. You would have serial numbers or whatever, part numbers or product numbers. But this is a primary key, and I have a foreign key here. Product is a foreign key in my sales that points to a product. Here I have another foreign key that says who bought which product, and the foreign key points to here, where I have the primary key of my customers' data, and CT is the additional data. You see the redundancy is gone. This is no longer duplicated. This is no longer replicated, right? So I've basically removed a bit of redundancy. Do you see that in that case, it would be a natural join? Yeah, it would be a natural join because in that case, the column names are the same, product, product, and customer, customer. So I would do it with a natural join. If the column names would be different, I would just use a theta join with either using or on. Okay. So in essence, what we want to say is that we prefer this to this. We don't like this, and we like this. So we could just say, okay, I like this, I don't like this, but the problem is that mathematically that doesn't give me anything because I have no objective criterion to say why I like this design and why I don't like this design. So I want to now give you mathematical tools that quantify and that tell you why this is good design and why this is bad design. Right? And this is what we call normal forms that give you that. So we need to define formally what it means to have a better schema, and the name for that, it's already advanced in a relational database course. It's called database design theory. Okay, so that was just the appetizer. So I told you that database design theory is about normal forms. There's plenty of normal forms. In fact, we even count them. There's the first normal form, the second normal form, the third normal form, the fourth normal form, the fifth normal form, the sixth normal form. There's some of them that don't have number, like the Boy Scout normal form, which informally has number 3.5 for some reason. And then we have normal forms that were invented later and that don't have numbers, right? But they have the names of whoever invents them. So we have a lot of different normal forms. I think probably 15 of them by now, 15 different normal forms. Normal forms are just a yes-no criterion. You look at the data and you say yes or no, it is in that normal form, right? And so the higher the number, the stricter it gets. The first normal form is pretty easy to get. The second, a bit more strict. The third, a bit more strict. And as you go higher, stricter and stricter and stricter. In typical bachelor's curricula in computer science, we teach the first 6. I would say it's maybe not in all university the first 6, maybe at least 4, but you can also go ahead and teach the first 6 normal forms. Don't worry, I'm not going to teach you the 6 normal forms because it can be also quite involved for every one of these normal forms to understand, because there's a lot of math to explain how it is. You have to get the intuition of each of them. You need to understand the algorithms that can turn a table into the right normal form and so on. So you don't have to be too much worried about this. I'm going to basically focus a bit more deeply on just 2 of them, which are the first normal form and the Boy Scout normal form, and then maybe give you an intuition for some others, but I'm keeping it accessible for non-computer scientists. But first, I have very good news. You already know the first normal form. Who remembers what the first normal form is? Or maybe I didn't call it this way, or I just mentioned that it was called the first normal form. Anybody on Zoom?
No, I'm not anything.
Who remembers atomic integrity? That's it. That's the first normal form. So that's a bingo. You check the box. You already know the first normal form. That one was easy, right? So as a reminder, we say that a relational table is a set of maps, plus when it fulfills 3 conditions: relational integrity, domain integrity, and atomic integrity. And atomic integrity basically means that whatever is in the cells is not atomic. It's these scalars that I told you about, right, in SQL, the scalars. So here we basically have stuff that are not atomic. Can you spot it? Column B. colon B, I use the JSON notation in that case, but these are JSON arrays. These are not atomic. 1, 2, 3, 4, 5 can be cut down into atoms. 1, 2, 3, 4, 5 would be the atomic values, but there's 5 of them in the same cell. So that's not, that doesn't have atomic integrity, right? Foo bar and so on. That's another example where I didn't use arrays here. I use objects. For whoever knows JSON, these are basically just, these are lists, and these would be maps, but nested maps, where we have complex types that are also not atomic, right? And even more specifically, tables in tables in tables in tables in tables. So this, and this do not have atomic integrity. So I can also say this, and this are not in the first normal form. So these are counterexamples. This is not in the first normal form. This is also not in the first normal form. So in the end, how do we get the first normal form in our definition of the relational tables, where we just need to restrict the set of values? When we say that each record is a map from strings to values, we just need to say it's a map from strings to atomic values, right? So that's the set of values that we call V. We just need to say that it doesn't have anything that's not atomic, right? So that's an example in first normal form. Who agrees this is in the first normal form? Right? It's atomic integrity. All the values in here, you can see there's 12 values in there, and these are all atomic values. There is no nested table, there is no object array or anything. There's just atomic values. There are strings, booleans, integers, and so on. So we only have atomic domains. So another way of putting it, it's flat. Every record of the table is flat. It doesn't have anything that goes deeper in it. No tables in the tables, no objects or arrays or anything inside the tables. So that is not in the first normal form. I'm just inundating you with visuals. This is not in the first normal form because we have structure in there, and we cannot have structure in the first normal form. That is in the first normal form. Okay. So who I want to see all hands raised? If I show you a table, any table, who now feels that they can tell me yes or no it's in the first normal form just by looking at it? Right, I suspect all of you, right? Okay. So now, when we specify a normal form, and that's true for all of them, the second, the third, the fourth, the fifth, the sixth, Boyce code, it also comes with some algorithm that allows you to turn them into the normal form. And that's typically what happens when something has tables in tables in tables in tables. You can actually apply an algorithm that turns it into something that is in the first normal form. For example, I can take this, which here has lists of customer quantity pairs, right, in that column. And I can turn this into this table that has the first normal form. I can do this. How did I do it? So I have, you see, John 1, Peter 2, Mary 1, John 1, Peter 2, Mary 1. But here, I just duplicate it. You see phone 800, it appears only once here. I had to duplicate it. And now I have 3 records where I duplicate this and then use this. Then I duplicate this. So John 3, Mary 1, I put in there, and I had to duplicate laptop 2000 and so on. So the trick to turn a table not in the first normal form with tables in tables in tables into the first normal form is just to duplicate those values enough times that it becomes atomic. Who sees that they store the same information, these two tables? Right. Awesome. And of course, you see the price to pay is that now we have duplicates, and you probably already see the alarm signals in your head: update anomaly, delete anomaly, insert anomaly, because the table on the right was exactly the one that was causing problems. So what does that tell us? Well, it tells us that the first normal form is not enough, right? If we just say we are in the first normal form, then we can still have problems. And this is why we have the second, the third, the fourth, and more normal forms that add further restrictions. Who is with me? Right? Okay, so I'm gently introducing more concepts. The next concept that I want to introduce is that of a table universe. It sounds fancy, but actually it's very simple. It just says that tables evolve over time. When you have a web shop and people order from your website, it changes the tables. So over the month, over the years, you're going to have plenty of versions of the same table. So that's exactly what's happened, right? So maybe at some point in time, the table looks like this, and then some records get eliminated or added, so it basically changes. What usually doesn't change, or at least more rarely, is the schema, right? So we have the schema, but there's multiple versions of the table over time. It changes. This is what we call a table universe. Right? Basically, it's kind of the theoretical set of all tables that you consider acceptable as part of your schema that you could get over time. So since we have a schema, that's the create table statement that you start with in PostgreSQL, right? You write create table, and then that enforces the schema. And if you ever try to have insert into with something that doesn't conform to the schema, you get an error, right? And if you do conform to the schema, it's going to update it. So we call them the valid extensions. The sets of maps, they are valid extensions if they respect the schema of the table that you have above here. So you can see these three respect the schema. They could go together with this. When we look at it a bit more formally, there is actually plenty of constraints that you have for this set of table contents, table extensions that you find acceptable. Some of them we already know. We want relational integrity, we want domain integrity, we want atomic integrity if we want to be in the first normal form. So I put these three as a Venn diagram, right, or an inclusion diagram. So I have here all my collections. Now I have those that have relational integrity, those that have domain integrity, those that have atomic integrity. So now I have relational tables, right? And within the relational tables, I might want to restrict further with check, unit, unique, non-null. You remember all of these constraints that you put in create tables? Who remembers them? Right? Unique, check, non-null. So that further restricts the tables that I accept, right? And in fact, I can even put more in there. And these are the normal forms that we are going to add. So functional dependencies are just the mathematical ingredients to it that I'm going to explain to you. So higher normal forms, higher because atomic integrity is the first one, and that further constraints, right? So it's really this idea that we want to constrain, that we want to put conditions on the tables that we want to accept as in my database. For example, if you try to have this, that's not going to work because that doesn't respect the schema, right? So that would break the relational integrity because you only have two values, but you have four of them in there, right? That is not allowed. Why? Because this is not a numeric. You see, that says price numeric. This is not a numeric, so that wouldn't respect the schema. And this one would not be allowed, but that's another reason. It wouldn't be allowed because me, as the designer of my web shop, do not want different prices for the same product. I see 400, 800, 850, 900. So as a designer, I would like to disallow this. But the problem is that I don't have a way of disallowing this with the tools that we've seen until now, right? How can I express that? I don't think I can use a check or unique, or that just doesn't work. We need something else. And that something else is the functional dependencies that I'm going to introduce now, right? So this is going to fit in that picture. Who is with me? Who is ready for the functional dependencies? Okay, so functional dependencies. You will see it sounds scary. It's actually not so scary. Well, this is scary. The slide is scary, but the visuals should be a bit easier. So let me just throw the definition at you first. So first, what do I need? What are the ingredients of that? Well, I'm looking at a table, at a relational table. I'm going to call it R, right? So I have a relational table. And I'm looking at two sets of attributes, S and T. These are just two sets of attributes. So maybe my table has the attributes A, B, C, D, E, and F. And S, I could take A and B, and for T, I could pick just E, for example, right? So these are just sets of attributes. For the sets of attributes, I use the letters S, T, U, and so on, right? And for A, B, C, I use them for attributes. It's only a convention to make it easier to understand, right? They could be called anything. So two subsets of attributes S and T within the schema of the table. So I'm saying that we have a functional dependency between T and S, and more exactly that T is functionally dependent on S. And I have this little notation right here with the arrow, S, right arrow, T, when this horrible formula applies. So what does that horrible formula say? It basically says that when I pick two tuples in my table, it might be 1,000 different tuples, 1,000 different records in my table. But if I pick two of them, whenever I pick two of them, if these tuples happen to match on S, meaning that on the set of attribute S, these tuples have exactly the same values, then that functional dependency tells me they must also match on T, on all attributes in T, right? Who already has an intuition looking at that formula? Maybe not a lot, right? This is why I have visuals. So first, before the visual, I replaced T, S, and T with actual sets of attributes. I just rewrote the same thing to give you an idea. So imagine that S is ABC and T is DEF. And I'm saying that DEF is functionally dependent on ABC. What that tells me is that if I ever find tuples in my table that match on A, B, and C, they have the same values for A, B, and C, then I conclude that they must also have the same values for D, E, and F, right? So we say that D, E, and F are functionally dependent on A, B, and C. And that's the visual. You see how that works in reality. So imagine that I want to look at the functional dependency. DE is functionally dependent on AB. How can I see that? Well, let's find two tuples that match on A and B. Do you agree these two tuples match? These two records match on A and B? Who agrees? Right? Foo bar, they match. So then I should watch, okay, do they match on D and E as well? Because they should. If this is true, then they should. Do they match? True, one, they match, right? Let me take another two tuples, another two records. Let's take this one. Do they match on foo bar? They do, right? These two records match on A and B. So we need to check if they also match on D and E, and that's the case, right? And so if that works for any tuples, whenever I find two tuples that match on A and B, then it's always the case that they also match on D and E. Then I can say that DE is functionally dependent on AB, right? Who now has more intuition, right? I would also say, because it's reading right to left, DE is functionally dependent on AB, I might also say AB functionally determines DE, which is just to read it from the left to the right, but it's the same thing. Okay, here's a counterexample, right? So that's the easy part. Finding that it's false is super easy. It's enough to find two tuples that match on AB and that don't match on DE, and that's done. You have your proof. So you know that's the power of math, right? If you want to say that, to prove that something is always true, that's going to be complicated. But if you want to say that something is not always true, all you need is a counterexample, right? So this is how math works. So if I want to prove that a functional dependency is not true, I just need a counterexample. All I need to do is two tuples that match on AB and that don't match on DE. That's enough. That's my counterexample. But if I want to prove that it's true, it really must true all the time for any two tuples. So that's a very strict condition. Quick question. Can you find a few functional dependencies in here? If I give you that table, could you tell me which set of attributes functionally determines which other set of attributes? Anybody? Anybody with their opinion? Can you find them? Can you spot the functional dependencies? So I'm just looking for this functionally determines this. Quick hint, it doesn't have to be two of them, could be also just one. I think we have one volunteer over there in the back. Sorry? Product and price, more precisely, product functionally determines price, right? So we can check. These two tuples have the same product. They also have the same price. These two tuples have the same product. They also have the same price. These two tuples have the same product. They also have the same price. These two tuples have the same product. They also have the same price, right? Who agrees that this functional dependency exists? Okay. Well, technically, you're going to tell me, but then we also have that price functionally determines product, right? You could also see it the other way around. That if they match on the price, they match on the product. But you see, that's just an accident, right? Because in my intention, I could also have two tablets that are worth 800 francs. That would be fine, right? So as a human, as a designer, the one that I care about is product functionally determines price. Doesn't? Yeah.
How about the customer and the city?
Yes, absolutely. The customer and the city. Who sees that? So the customer functionally determines the city. John, Zurich, Zurich. Peter, that's the only one. Mary, you see. Basel. Also here, by accident, the city determines the customer, but that's only because it's a small table. If you have an actual web shop, you're going to have many people from the same city, right? There's not a single customer in every city in Switzerland. So if the table would evolve, then the only one that we would consider is customer implies city, customer functionally determines city. So that's the first one. Product functionally determines price. These are singletons then, and customer functionally determines city. Who is with me? Who would now have enough intuition that if I show you tables, you could just tell me the functional dependencies visually? Right, okay, very good. So it's all about the intuition first. Okay, but first a little bit of notational cleanup, because if I have to write these functional dependencies on all my slides and every time I need to write the curly braces and the quotes of the attributes and so on, I'm going to lose my mind. So what we do typically is that we don't put the set notations, we just write it like this. We don't even put commas in the middle. We are just a bit lazy, and in the textbook we just write this, right? So A and B functionally determines D and E. It's only a notation thing. So now I can write it like this. I got rid of the curly braces and of the quotes. So product functionally determines price, and customer functionally determines city. And you agree, if I take this as an example, price functionally determines customer doesn't hold. And how I explain it doesn't hold, I just need the counterexample. And these are my two records that have the counterexample where they match on the price, they don't match on the customer. That's enough to say that this functional dependency doesn't hold. Who agrees it doesn't hold? Right? Awesome. So now, going to have lunch soon, but again, since it's Halloween, I'm allowed to show you scary things. It turns out that there is a criteria using the relational algebra with pi, sigma, and so on that gives you a characterization of a functional dependency. So that's not the definition, that's only a characteristic. It's another way to characterize a functional dependency. So I'm still looking at ABC functionally determines DEF. So how can I tell with the relational algebra that it applies? Well, I do this in that order. First, I'm going to pick some possible values for A, B, and C, right? Like foo bar 1 or whatever values I want for the actual values that would go in the cell, in the tuples for A, B, and C. And I call them F. So I have F.A, F.B, F.C. That would be possible values for these attributes A, B, and C. And now I'm selecting that sigma selection, that's the where clause of SQL. I'm selecting all of the tuples in my relation that have these values, FA, FB, FC, right? Then the next thing I'm doing is that once I have selected these tuples that have specific values, I'm projecting on D, E, and F. I'm only keeping D, E, and F. Remember that we are in the set of maps semantics. That's the kind of the default one, the chocolate flavor. So you agree there's duplicate elimination, right, in the set of map semantics. Who sees that if we have this functional dependency, that D, E, and F are determined by A, B, and C, then if I pick all the tuples that have the specific identical value for A, B, C, I select just these tuples, and then I project to D, E, F, who agrees it should be just one single possibility? It's a singleton. Who agrees? I have a visual for everybody else, but some of you agree. Let's see it visually. Imagine that I want to see that product functionally determines price. So I just pick one value. I could pick 800, I could pick 2000, I could pick 1000. So let's pick any of these. Let me pick, oh, sorry, I'm not doing, why am I looking at the price? I should look at the product. I should look at the left-hand side. So I pick a product. So I could pick phone, I could pick laptop, I could pick TV, one of the three. So let's pick phone. Let's pick phone as an example. So I'm going to have a selection on all the records for which the product is the phone. There you go, right? I select those that have a specific value, in that case, phone, right? I could also do it for laptop or TV, right? But I do it for phone. Now you see it coming, right? I'm projecting on price, duplicate elimination, only 800 is left, right? Who sees that now, right? Who sees it applies generally to any functional dependency, right? Okay, and you would do the same if you would do it on laptop, then you would just get 2000. If you do it on HDTV, you would get 1000, right? So this is just for the mathematicians. You can use that alternate characterization as a way to tell, right? Okay, and then check, because, but of course it would need to be true for any value, right? But at least for phone, it's true. And now you probably see why it's called functional dependency. It's in fact, we have a function from S to T, right? We have a function from S to T. So when we say that S functionally determines T, we basically are saying that the values that are associated with T can in fact be obtained as a function of the values determined from S. The physicists would probably write T of S here, right? Mathematicians don't do that, but physicists, they would write T of S in order to express that T is a function of S. Who is with me, right? And so here we would basically say that P, if we call the function P, price is a function of the product. There exists a function that maps the prices to the products. I can even give you the function, that is the function, right? That is a function, and I have a function such that the price can be computed with this function from the product. This is why it's called functional dependency. We could do the same for the customer and the city. I removed the city here, but if we had the city, I could do the same. Okay. Who is with me? Right? So I think that should be enough for today. So now you know, well, you know why we are doing that, because we don't want these anomalies. We want to do things right with a website. We need to express that we must have plenty of tables that each do one thing. And the first mathematical concept that we are going to use for the normal forms is the concept of functional dependency. So next week, I'm going to use these functional dependencies to define another normal form. Thank you very much for attending today. Enjoy your lunch, enjoy the exercise session. If there's anything you don't understand, you write us an email to the TA team, to me, to the Moodle forum, and we'll explain very gladly. So thank you very much, and see you next week at 10 a.m.